Okay, so I want to talk about Iwasawa theory for the symmetric square of an elliptic curve. So I will start, by setting the scene and talk about the Iwasawa main conjecture and Euler systems. So, okay, so the Iwasawa main conjecture. So, and Euler systems. Okay, so we let P be an odd prime. And we let V be a geometric periodic representation of the absolute Galois group of Q. So, which is the absolute Galois group of Q. So, and then attached, to this representation, we have the complex L function, LVS. So, there's the complex L function. Right, and then let me introduce some notation. So, we let Q infinity be the cyclotomic ZP extension of Q. So it's contained, in Q adjoint all the P power roots of infinity, cyclotomic ZP extension. So in other words, it is the direct limit of the finite extensions of order P to the n. So we let gamma be the Galois group of Q infinity over Q. So it's isomorphic to ZP, and we write lambda of gamma for the Iwasawa algebra, so for the algebra of measures on gamma. So it's the Iwasawa algebra. Okay. So then there is the following conjecture of Coates and Perrin-Riou, which says that there should exist a measure, so an element of the Iwasawa algebra, which interpolates the critical values of the complex L function. So let me state it in the following form. So we have the conjecture, so due to Coates and Perrin-Riou. So, assume that V is ordinary at P. one can actually weaken this assumption, but for simplicity, we assume V is ordinary. So assume that V is ordinary at P. So, and that L of V0 is a critical value. So then there exists a measure, so a periodic L function attached to V. So it's an element of the Iwasawa algebra, which has the following interpolation property. So such that for all chi, which is a finite order character of gamma, so we have the following interpolation properties. So, if we integrate, this measure against chi, so then up to an explicit non-zero factor. So we get the value of the L function of V twisted by chi, evaluated at 0, divided by some period. Okay. Now, the Iwasawa main conjecture, relates, such a periodic L function to a Selma group of the Galois representation. So to explain this, we let T inside V be a GQ invariant lattice. So we can then consider the object, which I denote by X Q infinity T. So what is this? Well, it is some Selma group of the Galois representation over the cyclotomic ZP extension. So we are looking, I mean, at the Selma group over Q infinity. So with values in the Pontryagin dual of T twisted by 1, I mean, all dualized. So here, I mean, this here means the Pontryagin dual. So, I mean, and here's the Selma group. I mean, at P, I mean, it has the Bloch-Kato local condition. Right, so I mean, this Selma group is a finitely, has a structure of a module over the Iwasawa algebra, and it is in fact a finitely generated module. So this is a finitely generated so module over the Iwasawa algebra. So, and I mean, for this, for modules of this kind, I mean, one has a structure theorem. Namely, if it is a torsion module, one can associate to it, I mean, a so-called characteristic ideal. So, and the Iwasawa main conjecture says the following. So it says the following, that so under the ordinarity assumption, I mean, on the Galois representation, that this Selma group is a torsion module so, and its characteristic ideal is generated by the periodic L function. Right, okay. So, and I mean, this conjecture, I mean, if one can prove this, I mean, it has applications to the Bloch-Kato conjecture. So for V by any character chi as above. So let me just remark, so note, so this is closely related, so to the Bloch-Kato conjecture. So for V twisted by chi, so for all chi as above. Okay. Right. Now, how does one attack this conjecture? Well, I mean, one usually attacks it, I mean, from two sides. I mean, say, the idea is, I mean, one can use Euler systems, I mean, to show, I mean, that LP of V is contained in the characteristic ideal. And then there are other techniques, I mean, to prove the reverse inclusion. So I want to talk about the use of Euler systems. So what is an Euler system? So it is a tool for attacking the Iwasawa main conjecture. Tool for also proving one inclusion. So of the Iwasawa main conjecture. So what is the definition? So definition, so an Euler system. So for the representation V is a collection of cohomology classes. So, well, I denoted by Z underline. So it is a collection, I mean, of cohomology classes indexed by the positive integers. Okay, so, I mean, where does Zm live? So Zm is an element of the first Galois cohomology group, not of Q, but of Q adjoins the mth roots of unity with values in T. So in other words, I mean, we have an infinite collection of cohomology classes defined over the different cyclotomic extensions of Q. And what we want is that they are in some sense compatible. So how does this compatibility work? So such that, so for all primes L, so we can look at the Galois co-restriction map. So from Q adjoint mu ML, so down to Q adjoint mu M. So, and two things can happen. So either the class upstairs is just sent to the class downstairs, so to the class Zm. So this happens if L divides M, or if T is ramified at L. So, or it is sent to PL of the Frobenius at L, so of Zm. So what is PL of X? So it is just the characteristic polynomial of Frobenius, so acting on the Tate dual of the representation. So, I mean, these here are, of course, I mean, precisely, I mean, the terms, I mean, which appear in the definition of the L function of the dual representation. So, I mean, in some sense, one should think of an Euler system as a kind of cohomological incarnation, I mean, of the L function of the Tate dual. Okay. Now, that's an Euler system. What is it good for? Well, we have the following theorem, which is called the Euler system machine. Which is due to Colli-Wagen. Colli-Wagen, and was then extended, I mean, by Cato and Rubin. So, which says, so we assume some technical hypotheses. So on the representation V. So, for example, so a large image. So then, so if Z is not the zero Euler system, I mean, clearly, I mean, if all classes are zero, I mean, it satisfies the norm relations, but that's not very interesting. So, I mean, if Z bar is not the zero Euler system, so then, so X, Q infinity T is a lambda gamma torsion module. So, and we get a bound, on the size of the characteristic ideal. So, I mean, of course, here periodic L functions don't enter yet. I mean, so that will come in a second when we relate the Euler system, I mean, to a periodic L function. So, and one also obtains a result for the Selmer group over Q. So, if the bottom class of the Euler system is non-zero, so then the Bloch-Kato-Selmer group over Q, so of our representation is finite. So, and one gets an explicit upper bound for its size. Okay, so I want to make a few remarks here, so which will be important in what follows. Namely, it turns out, I mean, we don't really need classes defined over all the cyclotomic extensions. So it is sufficient to have Euler system classes, so where M is of the form P to the J times N, so where J is any integer greater or equal to 0, and N is the square-free product of primes which are congruent to 1 mod P. I mean, this comes when one looks into the Euler system machine, I mean, that one actually picks out, I mean, a set of primes of this kind. So this N, a square-free product, so square-free product, so of primes, so which are congruent to 1 mod P. So, and one can thin this set out even further. And I will give an example of that later on. One can see in this set, so even further. Okay, right. So how do we get from this, I mean, to one inclusion of the Iwasawa main conjecture? So the answer is, I mean, via something called an explicit reciprocity law, which relates the Euler system to periodic L functions. So how does this work? So we let H1, so here's the relation, so two periodic L functions. So we let H1 Iwasawa psi of Q infinity T, so be the inverse limit, so over the cohomology groups, I mean, over the finite sub-extensions of Q infinity. So, and then parallel U has constructed a map, I mean, from this H1 Iwasawa into the Iwasawa algebra. So, I mean, if we have an Euler system, it will give rise to a class in here, because in the p power direction, I mean, the Euler system classes are compatible. So, and then parallel U has given a way of interpreting this class we get in here as an element of the Iwasawa algebra. So she defined what is called a regulator map. So reg P, so from the H1 Iwasawa, so into the Iwasawa algebra. I mean, this only holds under the assumption, I mean, that V is ordinary at P. I mean, otherwise you get a map into the algebra of distributions. Okay, so what is the general expectation? So that there exists an Euler system. So Z for V, so such that the image under the regulator of the Euler system is equal to the periodic L function. So if one has this, so this is called, so such relation is called an explicit reciprocity law. Okay. So and then, I mean, via the Euler system machine, so I mean, one gets that the periodic L function is contained in the characteristic ideal, say, of our Selmer group. So, and if Z1, so and if Z1 is not equal to 0, so one gets an explicit bound. Explicit bound, so for the size of the Selmer group over Q, so in terms of the value of the periodic L function. So LP of V at 0. And I mean, if 0 is a critical value, I mean, this he agrees, I mean, with the complex L value. Okay, so I mean, one example of this is Kato's work for modular forms. So Kato's work, so for modular forms, so he constructed an Euler system and proved an explicit reciprocity law when the representation is just a periodic representation attached to a modular form. Okay, so I mean, this is a general setup. Now I want to specialize to a periodic representation arising from an elliptic curve. So namely the symmetric square. Right, okay. So we specialize to the following case. So the symmetric square. Right, what is the setup? So we let E over Q be an elliptic curve. So which is not CM. So and ordinary at P. So and we let Vp of E be the periodic Tate module attached to E. So, and we let the periodic representation that we want to study is the adjoint representation of Vp of E. So, which explicitly, I mean, is the sim squared of Vp of E twisted by -1. Okay. So, I mean, so in this case, I mean, the conjecture of Coates and parallel U is known to hold due to work of Coates and Schmidt. So, Coates, Schmidt, so they constructed the periodic L function for this representation. Okay. So why is this an interesting representation to consider? Why would one want to bound a Selmer group here? So let me make some remarks. So namely that's the Selmer group for V. The Selmer group, I mean, for the adjoint representation, so is closely related to the deformation theory of V. So which is important in modularity lifting. And in particular, I mean, it featured heavily, I mean, in Weil's work on Fermat's last theorem. Okay, so I mean, there was some work, I mean, by Flach from the 1990s. So he constructed with some kind of partial Euler system. So I mean, he was not able, I mean, to construct a full Euler system, but he had a partial Euler system. So with which he could prove the finiteness of the Selmer group. So finiteness of the Selmer group, so of the representation. But he did not obtain a good upper bound. And I mean, this is then, so and of course there was no information, so over Q infinity. So I mean, he could not prove, I mean, anything about the Iwasawa main conjecture. So, and I mean, giving an optimal upper bound, I mean, was something that was essential, I mean, for Weil's proof of Fermat's last theorem. So, I mean, Weil's first tried, I mean, to construct an Euler system. But when that didn't work, I mean, he found an ingenious, I mean, other approach via Taylor-Weil's lifting. So Weil's, and then, I mean, Diamond, Flach, and Guo. So, I mean, they obtained an optimal bound. So for the Selmer group, so via Taylor-Weil's patching. So, I mean, the question that I want to address here is, can we resurrect, I mean, the first approach and construct an Euler system for the adjoint representation? So the aims of this talk are the following. So, I mean, the first one is to build an Euler system. Build an Euler system, so for the adjoint representation. So, and then relate the Euler system to the periodic L function. So to the Coates-Schmidt periodic L function, and then, I mean, obtain one inclusion of the Iwasawa main conjecture and an upper bound for the Selmer group over Q. So I will do it as follows. I will first explain an approach which doesn't work, but which gives some clue how one should modify it in order to make it work. So the idea, so the approach, I mean, that David and I followed was to exhibit the adjoint representation as a direct summand of a larger representation for which we could construct an Euler system, and then somehow, I mean, try and use that, I mean, to construct an Euler system for the adjoint. So the idea, so exhibit, so V as a direct summand of a representation for which we can construct an Euler system. We can construct an Euler system. Okay, so here, I mean, the first attempt is to take the Euler system attached to Rankin-Selberg convolutions of modular forms. Attempt 1, so Rankin-Selberg Euler system. Okay, so the setup is as follows. So we let F and G be cuspidal eigenforms. Well, for our purposes, I mean, it is sufficient, I mean, to restrict, I mean, to weight 2 and trivial character. But I mean, this is just for simplicity. I mean, in principle, F and G, I mean, can have weight greater or equal to 2 and, I mean, non-trivial character. So for simplicity, so we assume that they are ordinary at P. So, and we let J be any integer. So then we have the following theorem. So, which was first proved, I mean, by myself together with David and Antonio Ley. And was later generalized together with David and Guido Kings. So, namely, there exists an Euler system, so which I will call so the Euler system of valence and Flach elements. So it is attached, I mean, to this triple F, G, and J. So for the following representation, so it is the dual of the tensor product of the periodic representation attached to F and G. So twisted by minus J. Okay. So, well, that was the construction of the Euler system, and we could also prove an explicit reciprocity law to relate it to the Hida-Panchishkin periodic Rankin-Selberg L function. So plus a relation, so 2 the p-adic, so Rankin-Selberg L function. Okay. Right, so how do we apply this now? I mean, to the adjoint representation. Well, so by modularity, so we know that E corresponds to a p-adic cusp form. So Fe, so this is to a cusp form of weight 2. So, and I mean, this is done such that the p-adic representation of Fe is isomorphic to the dual of the representation of the elliptic curve. Right, so we now let f and g, I mean, be this modular form Fe. So we let f equal to g equal to this modular form Fe. So what do we get then? So if we get an Euler system, so for the following representation, so we get Vp of E, tensor Vp of E, twisted by minus j. And I mean, this will decompose and, as a direct sum. So we get here the sim squared of Vp of E, so twisted by minus j. So this is 3-dimensional. So direct sum, I mean, a 1-dimensional factor QP twist 1 minus j. Okay, so this is 1-dimensional. Okay, well, the Euler system behaves very well because depending on the parity of j, it will take values in either of the two summands. Right, so the result is very pretty. So proposition. So the Euler system takes values. So well, there are two cases. Namely, it takes values in the sim square factor. So, I mean, if j is odd, so, and it takes values in the 1-dimensional factor. So if j is even, well, that's fine then, right? I mean, we just take j equal to 1 and we are done. So j equal to 1, so we get classes. So in V, namely the sim squared, so of Vp of E, twist minus 1. Well, here's the problem. What we are getting here, I mean, we get cohomology classes with values, I mean, in the right representation, but the problem is the norm relations are wrong. Because the norm relations are those, I mean, where the, so the tame norm relations are those, I mean, where this polynomial PL of x has degree 4. It is attached to the wrong representation. So problem, so the norm relations have the wrong shape. Namely, so what happens? So if we look at the co-restriction, I mean, from Q adjoint, so mu ML, I mean, down to Q adjoint mu M. So I mean, of this valence and Flach class. So, I mean, this will be sent, I mean, to PL of the Frobenius et al. Acting on the class downstairs. So, but what is PL of x? I mean, explicitly, So it is the following polynomial. So I get 1 minus alpha squared over L squared x times 1 minus alpha beta over L squared x. So times 1 minus beta squared over L squared x. This here is the right factor. This is the one we want. So this here is the Euler factor for the sim squared. But then we get a parasitic extra term coming from this one-dimensional direct summand. So what is this? It's 1 minus L to the minus 1x. Okay. So here, I mean, alpha and beta are the roots of the Hecke polynomial. So are the roots of the polynomial x squared minus AL of E x, so plus L. Okay. So the question is, can we just sort of divide out this factor? I mean, can we somehow renormalize the Euler system classes so and get rid of this factor? And the answer is no. Because we now remember, so for the Euler system machine, I mean, we actually want to just look at those L which are congruent to 1 mod P. So, but those we cannot invert. So let me just briefly explain this. So if one looks into the Euler system machine, so what happens? We take L congruent to 1 modulo by P to the K. I mean, so for some K, I mean, sufficiently large. So, and we work, so we look at the projection, I mean, of our class. So we work in ZP, so in the group ring of delta L, so where delta L is the C log P subgroup. So of Z modulo LZ star. Okay. But this group ring is a local ring. So, but say this is a local ring. So, and what is the maximal ideal? So just the augmentation ideal. So just the kernel, so of the map, so into FP. Okay, so, and I mean, the problem is, I mean, that this one-dimensional factor is always going to lie, I mean, in this maximal ideal. So, and so 1 minus L to the minus 1, the Frobenius is always in this ideal. So is in the maximal ideal. So which means that we can't get rid of the parasitic factor just by renormalizing. Or of the parasitic factor. Well, I mean, we were quite unhappy with that. I mean, when we realized this, because we did have cohomology classes in the right representation, but I mean, yeah, there was this obstacle and there was nothing to be done. And then we thought of another approach. So this is attempt 2. Attempt 2. So we look at the Assay-Euler system. Okay, so the setup is the following. So we let F be a real quadratic field. So we write epsilon F for the character. So, and we assume that P is split in F. So we then let curly F be a Hilbert modular form over F. So, and I assume, again, for simplicity, and because we don't need anything else, I assume it's of parallel weight 2. So, and trivial character. I mean, again, this works, I mean, all in much greater generality. So we then have the following theorem, so which was proved by Taylor and Labesse. Namely that there exists a two-dimensional periodic representation attached to the Hilbert modular form of the absolute Galois group of F. So there exists a two-dimensional, so periodic representation, so which I will call VP of F, so of the absolute Galois group of F. Right, and we now look at the tensor induction of this representation, I mean, to Q. So we let V, so this is called the Assay representation. So it's just a tensor induction. So from F to Q of this representation, VP of F. Okay. So, and I mean, attached to this, I mean, one has a complex L function, which is the Assay L function. So of F. So, well, in the degenerate, I mean, this is a sort of just slight modification in some sense of the Rankin-Selberg case. Namely, if you think of Q direct sum Q, I mean, as a real quadratic field, I mean, you recover the Rankin-Selberg case. Okay, so we succeeded, I mean, in constructing an Euler system, I mean, for this representation. So here's the theorem. So, well, it was first proved by, together with David and Antonio Ley under some simplifying assumptions, and then generalized by Giada Grossi. So, so we assume so that F is ordinary. So at the primes, I mean, P1 and P2, so dividing P. So then firstly, I mean, there exists an Euler system. So for all J in Z, so there exists an Euler system. So which is the Euler system of Assay Flach elements, I mean, attached to the pair F and J. So for the representation, so we take the dual of the Assay representation and twist by minus J. So, and then we have a second part of the theorem. So that was, I mean, work, I mean, with Giada and David. So under the same assumptions, I mean, there exists a periodic L function. So which I will call LP Assay. So of F, so which interpolates the critical values of the complex L function, and it is related to the Euler system, so via Perry-Hughes regulator map. Okay, so we now want to specialize to the case. I mean, when the Hilbert modular form is just the base change of our elliptic modular form attached to E. So we now let F just be the base change, so of our form Fe. So as in the Rankin-Selberg case, the periodic representation is going to split as a direct sum of two representations. So VP Assay of F, so it will split. So the first factor is just as we want, namely again the symmetric square of VP of E. And then we again get a one-dimensional factor. So we get QP. So it is just QP twist 1, but that's not all. And this is what's going to make the whole difference. We twist by our quadratic character attached to F. Ah, some of you are smiling. So you have understood what the point is. So, okay, I mean, as in the Rankin-Selberg case, I mean, the Euler system will take values in one or other summand, I mean, depending on the parity. So, I mean, again, so Euler system takes values. So in either factor depending on the parity, So, and we take j equal to 1. So, and then what is the parasitic Euler factor? The parasitic factor in the norm relations so is going to be 1 minus epsilon f of L, L to the minus 1 times the Frobenius. Okay. And now, as I said, I mean, we can actually thin out the set, I mean, the set of primes, I mean, for which we construct cohomology classes for the Euler system machine. And we will now specialize to those, I mean, which are inert in the field F. Yes?
You have to twist on the sim square.
One doesn't. It's just, no, one doesn't. We have checked that. I mean, you can check it directly, I mean, just by looking at the complex L function. So we have the following lemma. So if L is inert in F, and L is congruent to 1 modulo P, so let me call this condition star. So then the parasitic factor is invertible. So the parasitic factor is invertible. So in this group ring. Okay, so in other words, we can renormalize the cohomology classes for those L to get rid of the factor. So we renormalize the classes so to get rid of the factor. And it turns out, I mean, looking at those primes is sufficient for the Euler system machine. Okay, so we have the following theorem, disjoint work, so theorem. So this is joint work with David. So we let R be the following set. So it is P to the J, so times square free products, so of primes. So satisfying our condition star. So then we get an Euler system. So we get an Euler system, so Zm, so for M in R, so for the representation V, so which is related to the p-adic L function, I mean, of the base change of our elliptic modular form Fe via the regulator map. Okay, so I mean, as I said, I mean, it turns out the set R, I mean, is large enough to apply the Euler system machine. So what do we get? We get that, we get that the Assay p-adic L function is contained in the characteristic ideal of the Selma group. Okay. So, and I mean, we also get an explicit bound for the Selma group over Q, I mean, in terms of the value of this L function at the value s equals 2. Well, okay, but this is slightly unsatisfying because this here is the wrong periodic L function. I mean, this here is attached, I mean, to our degree 4, to our dimension 4 representation. Well, before I explain, I mean, what we do about this, let me just make the following remark. Namely, there is an alternative recent approach, I mean, by San Giovanni and Skinner. So, I mean, they constructed an Euler system. So for the symmetric square of Vp of E, I mean, via a totally different method. And prove an explicit reciprocity law, and I mean, also get bounds, I mean, for the Selma group. So, I mean, of course, I mean, we are working, I mean, with a twist, I mean, of this representation, but I mean, these representations are related, I mean, by duality. So, I mean, either of them, I mean, will give this result. Okay, so let me now get back to the question, what do we do about this here? I mean, can we get rid, I mean, can we replace this here, I mean, by the periodic L function of Coates and Schmidt? So what about so this periodic L function? So of the base change of Fe. So, okay, so Summit will be very pleased, no? So, I mean, we observe, I mean, that we have a factorization, I mean, for the complex L function. So, namely, it splits, I mean, as the L function of the symmetric square of E at S. So times, I mean, L function, I mean, just for the character epsilon F, I mean, at S minus 1. Okay, and I mean, so in the Rankin-Selber case, I mean, Summit proved, I mean, such a factorization, I mean, for the periodic L function, and we can adapt his methods, I mean, to prove the analogous result, I mean, for the periodic Assay L function. So this is a theorem which is in progress. So which says that we have an analogous factorization for the periodic L function. So namely it splits, I mean, as the Coates-Schmidt periodic L function. So times the periodic L function attached to the character epsilon. Okay, well, that's fine. Question is, can we get rid of this? I mean, can we choose, I mean, F such that this here is actually a unit? And there is a very beautiful result. So, well, let me just sort of say, so this here is, so this is the analog. So this here is the analog. So of Dasgupta's result. So in the Rankin-Selber case. So, and I mean, proving this factorization is very difficult. I mean, because the periodic L function doesn't have any critical values. So one needs to use a rather ingenious argument, I mean, which uses that the Euler system, when J is so for the even twist, I mean, lands in the one-dimensional factor. Okay, so the question now is, so can we get rid of this? And the answer is yes, under certain circumstances. So here's the theorem. So which is due to the Korean mathematician Ryun. So he proved that given P, so there exist infinitely many real quadratic fields. So real quadratic fields F. So in which P is split. So, and such that the periodic L function is a unit. So, and P does not divide the value of LP epsilon F1. Okay, I mean, so what one uses there is the periodic class number formula, so which expresses this, I mean, in terms of some periodic invariance, I mean, of the field. So, yeah. Well, in any case, I mean, if we have this, so, I mean, then we know that LP of epsilon F, so is actually a unit in the Iwasawa algebra. So we can divide out, and what do we get? We get that LP of the symmetric square of the elliptic curve, so is contained in the characteristic ideal. Yes. It's possible that it is it the value at 1 or the end? No, it is. No, it doesn't. I think it's a normalization issue. So, yeah.
Oh, this is allocated.
Yeah, no, it's LP of, yeah, precisely. Yeah. Right, so we can divide out, I mean, so and we get one inclusion, I mean, of the Iwasawa main conjecture. So, and in progress, so we get an optimal explicit upper bound. Optimal explicit upper bound. So for the Selma group, so over Q, I mean, of the, well, for the size of the Selma group over Q with values in the dual representation twisted by 1. Thank you.